And from there, did I derive? No, I did not. So we had the mean flow equation, and we'll derive the equation for kinetic energy from there. That is what I'm going to do in today's class. But towards the end, I also showed that dui by dxj, any second order tensor, we can split it into symmetric and antisymmetric part. And the antisymmetric part, if it is contracted with something which is symmetric, then the net result is 0. And this you can easily show. If you cannot ask me, I will tell you. Okay. Also, some more modalities. I have given you this sheet today, homework to B and 2C, which is basic, or 2A and 2B, which is basically now to get you. You have started, a lot of you have been asking me that this term is not matching, this term is not matching. So to make it all uniform, basically you have to write the expression for ui prime, uj prime. And I have given it to you that this has to be written in the following form. So, and then the hint follow, and this was already told to you. First you write the equation for ui prime, uj prime. And this has to be done, I had already told you. You take the equation for ui prime, remove all the j's. If anything is summed upon j, call it k or l, best is to call it k. And then multiply that equation by uj prime. The same equation you copy down again, but interchange I and j. So that will become the equation for uj prime multiplied by ui. And then, so right now you have not averaged anything. It is the equation for the fluctuation. Okay. So then you add the two equations. That will give you an equation for partial by partial t of ui prime, uj prime. Still no averaging has been done. Now there, then what I said was, the hint says first write the equation for ui prime, uj prime. Second hint is keep in mind the continuity equation for the fluctuation also follows the continuity equation. That means partial uk prime by partial xk is equal to 0. So this you will need in one of the terms. There's a term partial by partial xk, ui prime, uj prime, uk prime. You'll get only two terms when you derive. But if you keep in mind partial uk prime by partial xk is 0, and you multiply it by ui prime, uj prime, that will also be 0. And then you can club everything in this form. So this is one of the tricks you'll have to play. And second trick will come in the dissipation term. In the dissipation term, this equation writes you nu times d2 of ui prime, uj prime by dxk, dxk. So what I've tried to show to you is that you write ui prime, uj prime, and take del square of by partial xk of this term. And this I've done the first part of it, take the first derivative, and then now you have to take a second derivative of this. When you take the second derivative, there'll be total 4 terms, because there's a product in each of the terms. And the 4 may say 2 of the terms will form epsilon ij, and other 2 are what you will get in your equation. And so the final term will come. So you play with this, you will be able to get this. And then after you do all this, you carry out the averaging of the ui prime, uj prime. Okay. And at one stage, you will get something like average of ui prime, average of uj prime, uk prime. So that will become 0 because uj prime, uk prime can be pulled out of the average. Average of uj prime, uk prime can be pulled out. Any average can be pulled out. So we'll be left with average of ui prime times average of uj prime, uk prime, but average of ui prime by itself is 0. So you will have to use these two tricks that pull the mean out. If there is a product, then you have to take its average. And continuity equation may have to be used more than once. Yeah.
This continuity equation,
Hmm.
isn't it only applicable for value of average of ui?
No, so, but then if you, it's also applicable for instantaneous.
So why is it?
Oh, because that's the continuity equation, that you start from that. If density is constant, then the mass, then what you get is, there are two equations you get, mass balance and momentum balance. And the mass balance is partial ui, instantaneous by partial xi is 0. So that comes from the continuity equation. And when you subtract the mean equation from the instantaneous equation, you get the fluctuating continuity. Okay. And also then you realize first you do this. Then there is a part 2b on the second side. In part 2b, we are playing again with some of these. See, what I've done is the right hand side of the equation, I've split it into different terms so that you deal with one term at the same time. You don't deal with too many terms. And this sum of the second terms have to be written in this form. And actually, the second part of the question is just if you do everything, you will get there is no question really, the second part. This is what you will get when you apply. So this is what you will have to get to. And what you do is, do it, maybe we can make the submission on Moodle so that you have the original derivation with you always. But finish this derivation. So I hope all of you have started doing it. But once you start doing it, you get confused because the terms are in many forms. So to make it into a standard form, this has been given out to you. This will take you some time, maybe a couple of hours. It's not that it will come out immediately. And sometimes if you make a mistake, it may be even more, you'll get confused, or you may got stuck in a wrong track. Even I got stuck. I was deriving this after a long time. And for 1 hour, I kept on thinking, how will this term come? So it happens with everyone. Once I've done it, now I can easily find out where the mistake was or what it was, but otherwise. ठीक है? तो इसको we will keep it as a submission. And we will put it on, I think all of you upload it on Moodle. So we keep it what? After mid semester. तो mid semester में तो फिर पूछना भी है तुमसे भाई. तो इसलिए, so mid semester के बाद तो नहीं होगा. When do we do it? By Thursday or Friday next week? I think you must have already started this. अगर एक बार 1-2 घंटे बैठोगे हो जाएगा, तो इसलिए इतना परेशान मत हो यार, करना तो है ही ना सबको. तो वी कीप इट नेक्स्ट वेंसडे रखें. नहीं, वेंसडे तो होती नहीं क्लास. ट्यूसडे या कभी भी रख सकते हैं वैसे तो, नाउ बिकॉज इट्स टू बी अपलोडेड. लेट्स कीप इट थर्सडे. नहीं तो सबमिशन तो ले ही नहीं रहा मैं मूडल पे. या सबमिशन करना है तो फिर जीरोक्स सबमिशन करना, या कीप अ जीरोक्स कॉपी विथ यू. लेट्स कीप, इफ यू वांट टू सबमिट देन कीप अ कॉपी विथ यू. हाँ, फोटो खींच लो या जीरोक्स करा के रख लो, जो भी करना है. तो सबमिशन कर लेते हैं, ठीक है. फिर सबमिशन भी कीप इट ऑन फ्राइडे, बट नो एक्सटेंशंस देन. तो इस पे एक ये लिख देना कि फ्राइडे का वो, उसमें जब ये डालोगे ना कि सबमिशन ऑन फ्राइडे ऑन पेपर, कीप अ जीरोक्स कॉपी विथ यू फॉर योर रेफरेंस. नहीं, कौन सा वाला? नहीं, पिछली बार यही तो था, इसी का ही था. ये उसी को ही करवा रहा हूं, तभी तो 2A 2B इसी का ही है ये. ओके. So now we start. Yeah. हाँ, लेक्चर 14 है 15 है? या हाँ, मैं लेक्चर ले आऊँ क्या सामने?
हमने जो टर्बुलेंट काइनेटिक एनर्जी लिखा था और फिर वो
हाँ.
एआईजे को आंसर पेपर का डिविटोरिक में लिखा
हाँ.
था. तो एआईजे आपने ऐसे लिखा.
आज इफ यू डोंट माइंड विल कंटिन्यू. असल में एवरी टाइम समबडी नॉक्स आई थिंक देयर इज अ क्लास, बट इसमें क्लास नहीं होती. तो विल गो टिल अबाउट 15-20 मिनट्स मोर. ठीक है ना? बिकॉज इफ आई, so there's a doubt is, if you split a tensor into isotropic and deviatoric part, so Iij is equal to AII by 3. So I had asked you, I had said this that dii is 0. And since we are having this out, let's just show this. So dij will be equal to now here A is a general tensor. I have not made that it is symmetric or anti-symmetric. अभी एक मिनट, अभी तो मैं dij लिख रहा हूँ, ये तो आई है ना, तो आई तो मैट्रिक्स होगी. So this is dij. Are you comfortable? Now what is dii? Sum of all the diagonal terms. नहीं, comma in here, it's dii. ठीक है ना, so straight away. So this implies ठीक है, okay, no issues. अच्छा, but you should get the doubts clear rather than just think it's so obvious or it is easy. Why should I not get it? It's best. Okay, so now we start from the. We had started from the mean flow equation. Our mean flow equation was, in fact, this I had written in the last class, so I'm repeating this. I don't know whether I should repeat it or not. We are assuming that density is constant, so we'll pull it out of the brackets, etc. whenever we like. And Tij was minus P delta Ij plus 2 mu this is where we started from, and then we said let's now write the equation for mean kinetic energy, which will be equal to half of ui comma ui, and this we said we will call it as k. And if you look at the, I think I showed this in the last class also, if you look at the total kinetic energy, this will be equal to mean of ui plus ui prime multiplied by mean of ui plus ui prime. Half of this or is equal to अच्छा अभी देख लेते हैं, एक मिनट देख लेते हैं. So this, when you write it, this will become equal to half of this. I have not taken any mean. This is a total kinetic energy plus ui prime mean of ui 2 times plus ui prime ui prime. This is the total kinetic energy. Now if I take a mean of this, this will become half of and the first term is what we are calling as the mean kinetic energy. The second term we are calling as the turbulent kinetic energy. Because the other terms will become zero when you take the mean. When you take the mean of this quantity, mean of ui will go out. In fact, this is what will happen in some of the equations when you derive. If you pull the mean out, mean of ui prime itself is zero. If there's a mean of two turbulent quantities, two fluctuations, that will not be 0. Product of that. But this will be 0. So that's how we got this. So this term, in fact, I remember, I think I wrote it last time. This is what we call as small k. This is capital K. This is small k. This is turbulent kinetic energy. I realized I called it TKE, but TKE could also mean total kinetic energy, but that is what it does not mean. It means only the turbulent kinetic. So this we were there last time. So now the equation for K, this becomes rho times plus mean of uj Should there be a half also? No. Tij contains the halves or no? Because mean energy equation is this. So all I have done is multiplied this by mean of ui. So I multiplied, so first term becomes ui dui by dt. So it will be equal to, half will come. So that's fine. This is what I will get. Because in this dui by dt, a 2 will come, but when you write the kinetic energy, the half comes. So that's why the 2 and the half get absorbed. And this last term just becomes ui tij by dxj, mean of ui dxj. Now this term which we have, this term I write now d by dxj of tij times mean of ui can be written as, so now I'm trying to just play some games. I express this term using this notation. So therefore, the right hand side here will become rho times, I'll just write it again, dk by dt plus mean of uj dk by dxj is equal to, now I add this term, is equal to d by dxj of tij mean of ui minus tij So the right hand side I have just written it as a total derivative minus the second term, because that's what the product will involve. Okay. Now we often are doing, we will do these things quite often. And one of the things what you realize is that you will get terms like, which is a d by dxj, a spatial derivative of a whole quantity. And one of the indexes is common, which means it is a divergence. A common index means you are summing up on this, so this is a divergence. Okay, so let's first have a look at this before we move ahead. Wherever we have this d by dxj of I've just put tijk as some sort of this thing. Now, this is what I call, now here what we look, so there is j in tijk and partial by partial xj. This implies it's a del dot. D by dxj is del. And when there is a common index with ijk, that represents a dot product. Okay. Because by itself, del will raise, a del of a vector is a second order tensor. If I take dui by dxj, ui is a vector. When I take a d by dxj, it becomes a second order tensor. Okay. But when there is a divergence, if I take dui by dxi, that is a scalar. So that means divergence means two indices are contracted. So if the original quantity was of order n, the divergence will be of order n minus 1. Because you are summing over this, so two of these indices get contracted. Now, the physical significance of the divergence is, if I have a volume integral of a divergence term, that means I have this volume, I take a volume integral of d by dxj of tijk dv, which is equal to the volume integral of if the volume is not changing with space, then this derivative can be pulled out of the volume. That means the volume which I am choosing is a fixed volume. Then because this integral is on volume, and so I can pull it out if the volume is fixed. So I get it in this form. And what am I getting to? Which theorem will I use? The Green's is called in some, but mainly it's called the Gauss divergence theorem. So by Gauss's divergence theorem, this volume integral of tijk dv will become surface integral of tijk nj dA or ds, whatever you call it. And let me tell you what this means. So first I have written the theorem. Okay. So now what this tells you is, this is the volume. The left hand side is a volume integral. Volume integral means what? Whatever is the integrand, you calculate at a point, multiply it by the volume, add it up over the entire volume. That is what an integral is, summation. So when you say integral dv, I choose a small point, choose a small volume dv around it, whatever is the integrand, multiplied by dv, and then do it for the entire volume including the surface, add up everything, that is the volume integral. But what it tells me is, this is equal to the surface integral. That means, now if this is the surface S and I choose n is the outward normal, then this volume integral is equal to the surface integral of this quantity times nj dA. Okay. So in fact, or I could even write it as, or volume integral of d of tijk by dxj dv is equal to surface integral of. So that means to calculate the right hand side, I don't have to go inside the volume. I only have to travel all along the closed surface. Now this is in general, if it's a three-dimensional surface, then I have to go all around the surface. At each point, outward normal is vector n. I take a dot product of n with tijk, because there is a j common. So that's why I'm saying it's a dot product. And sum it only on the surface. And that will give me the volume integral. Okay. So this is first the significance of Gauss's theorem. Very powerful thing, can be used for any quantity. In fact, even this need not be a divergence. This could even be a gradient. Then also this theorem works. Okay. But now the point which I am coming to is that if Tijk is 0 on the surface, whatever this quantity is. So now, and Tijk is only used as a representation. It could be a scalar, it could be a vector, it could be anything. Okay, I've just used Tijk so that you realize it can be used for any quantity. So now, if this quantity is 0 on the surface, what it tells you is the divergence of this term is 0. So if this is 0 on the, so that means this quantity which we have, partial tau ijk by partial xj, what does it do? It redistributes Tijk within the volume. That will be the role of Tijk, of this divergence of Tijk. That this quantity will just distribute Tijk within the volume. Nothing will come from outside. So whatever exists inside, it just will be redistributed within the volume. That is the role of Tijk, and that's why this term is also called the transport term. So it does not create anything. Whatever was existing inside this volume, it just redistributes, splits it in like that. So that is the role of the divergence. And so, yeah, 1 minute. Yeah.
The way you have interpreted the divergence theorem,
Yeah.
basically electrostatics, we also use the Gauss theorem. Right?
Yeah.
So in that, we interpreted it as whatever that comes in, the same amount
Goes out. So here what it says is if nothing is coming in, then what I'm trying to see is the effect of this term. See, probably there when you look at the Gauss's, so what it does is that this term, if something is coming in, if this is not 0, then of course whatever is coming in, this term will distribute it within the volume. But if this term is 0 on the surface, that means from the surface nothing is coming in. Then the role of this divergence term will be to redistribute Tijk within that volume.
but it can be 0 such that X amount comes in from this part of the
Yes.
and X amount goes from the
Yeah. Yes. But overall, if nothing is coming in, see again, then what we are talking of, this partial Tijk by partial xj is at each point. So then such a balance will also take place on dV. So if something is coming in from dV, it also has to go out. Okay. Because so So now let us look at to explain concept simply. Look at pure shear flow, which means velocity vector, mean velocity is equal to u1, which depends only on x2, or in fact this x2 can be taken out. It really doesn't matter. So u1, mean u1 is only a function of x2. Mean u2, mean of u3 are 0, and averages of any other quantity with x1 and x3 are 0. Obviously, we don't say u1 because mean of u1 is changing with x2. So this is, and mean of u1 also is not changing with x1 and x3. All other quantities, all averages will only depend on x2. And if the flow is also stationary, then the time averages will also be 0. So now let's first write the equation rho partial k by partial t very simple equation we have got. Right now we have not expanded Tij, so therefore this term becomes equal to Tij ui minus of Tij. I've just copied that equation. Now, how do we expand this? Now, one thing I have often seen when I ask people to expand the energy equation, or this is the mean energy equation, so this is quite straightforward. But even when I ask students to expand the turbulent kinetic energy equation and write the component, now people write one component, two component, and three component. That is wrong, because this is an equation for a scalar. So if you see, each of these terms is a scalar. Scalar means, so let's look at this. This is k, there is no index. Here j is a repeated index. In this term, I and j both are summed upon. I is summed with here, j is summed upon here. Similarly, I is summed here, j is summed here. So this is a scalar equation. So you can't talk of a kinetic energy equation for x1 direction, for x2 direction, for x3 direction. It is just one equation. And this is a very common mistake students make. And if that happens, I think you have really not learned any basic in this course. Because this equation is for a scalar. Now, if we have to expand it for this case, how will we expand this? We will write first j as 1, let's say, and sum over I, and then sum over j. So I'll painstakingly let me do it for one term. Other terms I will leave you to. So suppose we want to expand d by dxj of Tij mean of ui. Okay. So this will be equal to, first say partial by partial xj. Let's sum over I first. So it will become T1j mean of u1 plus T2j mean of u2 Is everybody with me? We have summed upon I. So wherever there was I write it as 1, I write it as 2, I write it as 3, and leave the j as it is. Now, d by dxj of T1j, this will again contain 3 terms. When j is 1, when j is 2, when j is 3. Yeah.
putting chain rule first. Because then the del of the mean of u by del xj
Huh.
will give only one non-zero term, which will be
Okay.
del of u1 divided by del of x2.
Huh.
Then we get the other three terms of del of Tij divided by del of.
But basically you will be then, are you sort of reverting back to this form Tij dy by dxj? See, I want to keep it in this form because there is a reason why I'm doing that. But see, this is just straightforward. Once you start doing it, I'm just, so far we have not done it even once. So that is why I'm doing it. But this normally, if I will not do it in a class. And see, now what happens is, and as he rightly said, U2 and U3 are 0. Mean of, there's no U2 component, there's no U3 component. So let me first straight away take them to be 0 if I have to simplify. If it was general UI, then I have to do the entire thing. But here, since I have told that U2 and U3 are 0, and U1 depends only on X2. So that means I only have to take J is equal to 2. Because it is T1, let's expand it. It's not like this. So this will be equal to d by dx1 T11 U1 plus d by dx2 T12 U1 plus d by dx3 T13. And this term d by dx1 is 0, d by dx3 is 0. So this just becomes equal to d by dx2 of T12 mean of U1. अभी मैं सिंपल क्या हुआ बताओ पूछो लास्ट में U1 होगा बट वो 0 हो रहा था इट शुड बी U1. So essentially it leads to this term. This is, it should be, I've just gone through it actually, would have left it, but del xj of T11 आप हाँ हाँ तो T11 क्या है T11 भी तो सारे मीन्स ही हैं T11 is consists of only mean quantities. Okay, so that's what you will get. So this is now similarly, so that means the first term and Tij and since all of you are saying that this is straightforward, I will just, now this doesn't come by putting I is equal to 1 and j is equal to 2. In general case, it may not be as simple as this. But here, because u1 is only a function of x2, so you will get it in this form is equal to t1 to du1 by dx2. Actually, you are supposed to expand it like this and then check. But that is what will happen to the second term. So what we are left with is, and now, so these two things for the shear flow, we put this in. So now this is our basic equation. Now we are saying the flow is homogeneous in other directions and in other than x2 in x1 and x3, and we have d by dt. What happens to this term? Will it be 0 or non-zero? K is a mean, so it will be 0 because it's a stationary flow. Now this term will become u1 dk by dx1 plus mean of u2 dk by dx2 plus mean of u3 dk by dx3. So what will this be? No, but it's multiplied by what? u2. What is mean of u2? 0. So whenever you look at it, either you put this as u1, j is 1, then you get dk by dx1, which is 0. Okay. So this term, both of these will be 0. Is that clear to everyone? For this simple flow, u1 function of only x2. So I'm telling you how to simplify. No. So the right hand side is there. Let's look at the right hand side. नहीं कैंसिल कैसे होगा अभी देखते हैं. So let's see. So this becomes equal to, in the right hand side actually there will be something which will not cancel out because there's a d by dx2 है और यहाँ पे भी see d by dx2 is not 0 ना, d by dx1 is 0, so there's a d by dx2 and there's a d by dx2. So for the simple shear flow, the K equation simplifies to 0 is equal to partial by partial x2 t12 mean of u1 minus t12 du1 by dx2. Okay. So now let's try to give some meaning to this, each of these terms, and then we will split this equation up into the two parts and we will eventually get the conclusion which you just said without realizing it probably, that equation of mean K will not give us anything very specific. It will give us only that information which we get from the mean energy equation. That's the conclusion we will get to, but it will be in the limit when Reynolds number is high. So let's see that. So here what we do is, to understand this first term, let's look at a square element. At the center of it, at this point, let the mean velocity be u1 and this actually is a mean t12 be t12 here. So on this, at the top, we have this quantity will be u1. So this is delta x2. This is delta x1. So this will be u1 plus I am expanding u1 and t12 in a Taylor series. So the u at the top face will be equal to u1 plus partial u1 by partial x2 delta x2 by 2. Because I have taken u1 at the center. Had I started it from the bottom, then it will become the same thing without the 2. And similarly, t12, which is the shear stress on the top, will be t12 plus partial t12 by partial x2 delta x2 by 2. Now, what will these values be at the bottom face? Let's try to see, and I think you should be able to write this down. What will happen to this? U will be in the same direction, but by our notation, the shear stress on a negative face, we define it as positive on the minus direction. So, on this face, we have mean of u1 minus partial u1 by partial x2 delta x2 by 2, and the shear stress which is t12 will be t12 minus partial t12 by partial x2 delta x2 by 2. This is the shear stress. So I've expanded things in Taylor series and just use the sign convention. What the sign convention says that if the normal is pointing in the positive direction, then the positive stress points in the positive direction. And here the normal points in the negative direction. So therefore the positive stress will point in the minus direction. That is the sign convention. That's how T12s are defined. And this follows from the solid mechanics course or where we define shear. Fluid mechanics course. So, Okay, so this is what we have. Now what I'm trying to do from here is I'm trying to find out the total power on this element due to T12. What is power? Force dotted with velocity. So the total power on this element due to T12 will be equal to whatever is T12 here times the velocity here plus T12 here dotted with the velocity here. So now because these are in opposite directions, I will get a minus. Okay. So when I write this total power, now there are no vertical forces. T13, etc. are all zero. The only force is in the horizontal direction. And so, and T13, even if it is not zero, but then U2 and U3 are zero. So even it's possible T13 may not be zero because they are shear stress components, U1 prime, U3 prime there. They may not be zero, but then the velocity is only in the U1 direction. So therefore, because I take a dot product, I only go with the one direction. So total power on this element is equal to, let's write this down. So total power will be equal to, let's first write the force on the top face, T12 plus partial by partial x2 of T12 times delta x2 by 2. And this is stress, so I have to multiply it by the area to get the force and multiplied by the velocity u1 plus du1 by dx2 times delta x2 by 2. And this is on the top face, and from there I have to now subtract T12 delta x1 x3 होगा सर, multiplied by mean of u1 minus x2. And this, when I do my algebra, leads to T12 partial u1 by partial x2 plus u1 dt12 by dx2 times delta x1 delta x2 delta x3. And this I can write it as d by dx2 of T12 times u1 delta. So this gives me this term T, this gives me the total power which is generated by T12. But this again, as we recall, this term, because it's a total derivative of this term, this will basically be doing the job of redistributing the power or redistributing these stresses which are their mean stresses within the volume. The other term, when we look at it, so this is the first term, so this is equal to, and total power per unit volume, this is equal to partial by partial x2 of T12 times mean of u1. Now, there's a second term which is important and which is called the rate of deformation work, and which is work done as the particles or as the fluid gets deformed. And to get this, we follow the mean particle and at the center and fix reference frame there. So in this frame, mean kinetic energy will be equal to 0 because we are moving with the mean velocity. And this is done to isolate deformation work. That whatever is the extra velocity compared to the mean, what is the work being done by this extra velocity? We want to find that. And so here now, if I draw this element again, so here we have mean of u1 will be 0 in this reference frame, and it has a shear stress of T12. On the top, the velocity will be equal to du1 by dx2 times delta x2 by 2, and the shear stress is equal to T12 plus partial T12 by partial x2 delta x2 by 2. And here the mean velocity is partial u1 by partial x2 now times delta x2 by 2, because there is a minus sign here, so I write it like this, and this will be equal to T12 plus so now when I calculate the rate of work done here, what I'm going to get is T12 plus partial T12 by partial x2 times, अभी करता हूँ एक मिनट, this is the shear stress multiplied by delta x1 delta x3 and multiplied by the velocity. Velocity is equal to partial u1 by partial x2 delta x2 by 2. And from here to this we add T12 minus partial T12 by partial x2 delta x2 by 2 times the force, which is area, times du1 by dx2 times delta x2 by 2. So basically we calculate the rate of work done as seen from the point of the center line velocity, and this work done, yeah, नहीं यहाँ पे क्या है कि वो du1 by dx2 है क्योंकि हम मीन पे हमें देख रहे हैं, तो वो भी नेगेटिव हो जाएगा ना, du1 by dx2 जो है, there is a negative sign with this also, and because वहां पे जीरो है तो इसीलिए मैंने इसको डायरेक्शन ही उल्टी कर दी इसकी,
नहीं मतलब T12 वाला तो नेगेटिव, T12 माइनस,
T12 माइनस होगा, अच्छा हाँ ओके, सेकंड वाले में तो माइनस ही लिखा है मैंने, हाँ ये अच्छा यहाँ माइनस लिख दिया, अच्छा फिगर में गलत लिख दिया, ठीक है, थैंक यू, ठीक है. So this when you calculate, this turns out to be equal to T12 du1 by dx2, and this is the second term on RHS of K equation. So this second term represents the rate of work done by deformation. The extra part of the velocity which is there, that is doing this work, and this in a general sense, this will be, we have shown this, This is written as Tij, and this I am not expanding it, but in a general sense, if this is only for the simple case, but in general, this will be written as Tij dui by dxj. And here we can play a bit of gamble. I can write this as equal to Tij times mean of Sij plus mean of omega ij. I can break it into symmetric and antisymmetric part. And the reason for doing that is I know Tij omega ij will be 0 because this is antisymmetric. So this I can basically write it as equal to Tij mean of Sij. And now what we will have to do is, so we have done this Tij Sij part. Let us expand this. So Sij we know. What was Tij? To expand this, I will have to go to the start of the lecture where I said what Tij was. So now let's try to, we will write Tij Sij. So we have to put Tij Sij here, Sij here, Sij. Okay, so that's what I'm going to do. So we write Tij mean of Sij. So this will be equal to, I'll copy down from my notes what was Tij first. Minus P. So this I'm copying from page 1, the top of the lecture. Plus. थोड़ा ऊपर स्क्रॉल कर और ऊपर कि ठीक है. हाँ. Yes, it has. Yeah.
We put total differential of T highway U P of uj
हाँ.
because you said that there is no variation in any other direction other than x2.
हाँ.
So is that really true? We have
For ui prime, uj prime. So see, that is what, when you say the turbulence is homogeneous in x1 and x3, then that will mean all averages with respect to x1 and x3 will be 0. They will only change with x2. So ui prime, uj prime is going to vary only with the x2 direction in this case. So that is why I will get. Okay. But not otherwise. So maybe I may give a slight, if there's a slightly more general case where everything depends on x1 and x2. Let's forget x3. And if I ask you to write the equations, I think you should be able to, there'll be more terms now. So now you have mean of u1, mean of u2, function of x1 and x2. ठीक है ना, मैं एग्जाम अभी से बता रहा हूँ. तो उसको सिंप्लीफाई कैसे करेंगे हम? वो ज़्यादा लंबा नहीं होगा, 2 घंटा भी तो मिलता है. तो लेट्स सी, मैं करके देखूंगा खुद मुझे कितना टाइम लग रहा है. आजकल आई हैव रियलाइज आई एम नॉट एज स्मार्ट एज व्हेन आई वाज डूइंग ऑल दीज थिंग्स, सो इट टेक्स मी अ लॉन्ग टाइम. तो जितना मुझे लगेगा उतना ही मैं सोचूंगा, तुम लोगों को लगेगा मे बी स्लाइटली मोर, not too much, but because you people are smarter at it summing up indices or making shortcuts, which I am not. So anyway, so mean of omega ij is not 0. Tij mean of omega ij is 0 because Tij is symmetric, omega ij is antisymmetric. Yeah. So Tij, Uij, so by itself omega ij is not 0. But in this case, obviously mean is not 0 because du1 by dx2 is not 0. So you're right, but overall when you contract it with Tij, it will become 0. Now इसको कैसे सिंप्लीफाई करेंगे? दिस इज इक्वल टू, नाउ फर्स्ट टर्म क्या हुई? माइनस पी डेल्टा आई जे एस आई जे. हाउ डू आई सिंप्लीफाई दिस? डेल्टा आई जे मल्टीप्लाइड बाय एस आई आई. ठीक है ना? सो द फर्स्ट टर्म बिकम्स this. Second term is 2 mu mean of Sij, mean of Sij. Can't do anything. Third term minus rho second two I've just copied. Now what is SII? So SII is what? Half of dui by dxj plus duj by dxi. So I put I is equal to j. So I get dui by dxi plus duj by dxj. So 0. For incompressible flow, SII will be 0. So this is 0 for, because d mean of ui by dxi is equal to 0. Okay. So now when I feed this in, you get 0 is equal to, so the kinetic energy equation gives you 0 is equal to d by dxj of Tij times mean of ui plus 2 mu Sij minus rho ui prime uj prime Sij. एक मीन भी है. So this is the equation which we finally get. Now the first term, as we have discussed, will be a redistribution term. What do you think the second term represents? What physical quantity? Viscous dissipation, because there's a viscosity mu involved. So it represents how in a mean way the velocity is dissipated into heat. Or how the kinetic energy, this is the equation for kinetic energy, how the kinetic energy is dissipated into heat. Now there's a new term, ui prime uj prime mean of Sij. Now Sij is the mean velocity part and ui prime uj prime is the Reynolds stress. Okay. So now this total term, and we have also shown, or at least observed, we don't have a proof for that, that ui prime uj prime in general is negative. When we talked of the average, that there's a negative correlation between u1 and u2, or u1, we talked specifically for u1 and u2. So here, of course, if we make it, then this will become u1 prime u2 prime mean of S12. Now this term, this represents how the mean turbulent energy or mean velocity gradient is getting converted into Reynolds stresses. This is an interaction between Reynolds stress and the mean velocity gradient. Okay, this is the mean velocity, this is the Reynolds stress. So this is the only term which is telling you the how turbulence is interacting with the mean flow. And this term is called production of turbulence. This term will be referred to as production. Okay. 2 mu Sij is what we will call as the dissipation term. And this will be referred to as the production term. So, sorry. Rho times mean of Sij ui prime uj prime. This is what we call as the production of kinetic energy. And 2 mu Sij, this is termed as the dissipation of K Now, if we look at small u, this is the sort of order of magnitude analysis we have been doing, that in a turbulent flow, firstly, what we realize is the mean velocity gradient. The fluctuations are of the same order as that velocity. So we write it as u, and if L is the length scale, so the mean velocity gradient will be of the order of u by L. The fluctuating turbulent kinetic energy will be of the order of u square. If u represents maybe, let's say, root RMS of the velocity fluctuations, u1 something. So this term is of the order of rho u cube upon L. If I look at 2 mu Sij by the same logic, the order of magnitude of that will be equal to mu times u square upon L square. I have ignored the factor 2. It is of order 1. Now when you look at the ratio of these two, and again this is what we have seen probably in your homework also, which you have submitted to me and which we will discuss tomorrow, at least the how to do this. So the ratio of these two terms, so ratio of, अभी कल की क्लास का डिस्कस कर लेते हैं, अगर करनी है तो करते हैं, नहीं तो फिर कभी और कवर करेंगे. Production to dissipation term, this is equal to rho u cube upon L divided by mu u square upon L square. This is equal to and if Re is large, yeah,
You can say that for large array, the total power received by that blob
ah,
is turbulent kinetic energy.
yeah. So or the other way around, that whatever is the production of the kinetic energy, that is redistributed. And so, in fact, that is what I was coming to. Let's go back to the total picture where we started from, or what we did in chapter 1. What we said was turbulence is there are large eddies there, and then they keep on breaking into small eddies. And we finally said that the dissipation takes place at the smallest scale. We didn't prove that. To some extent here, now we are saying that the equations also tell us the same story. If I look at the equation of the mean kinetic energy, what I get from there is that the production term is a much higher order than the dissipation term. So therefore, whatever is produced as kinetic energy, it just keeps on getting redistributed, which Taylor called was the eddies keep on breaking and breaking into smaller eddies. So that is what is happening, and dissipation is not important at the large scale. So, yeah. So what I was saying was, what we started off with, or what picture we produced, we are now sort of verifying that from the equations also. Yeah. No, we are the mean energy.
So, dissipation terms about, you have signified it as small k, which
No, see, what I have done is, what I have used here is that the order of magnitude of the turbulent energy is of the same, or turbulent velocity, the order of magnitude is of the same order as the mean velocity. That the fluctuations, while they are of the same order as the mean velocity, because we are using the mean velocity gradient as u by l and turbulent fluctuations as u. See, here that is what we are doing, that Sij is being scaled as u upon l. Sij is a mean quantity. In fact, I forgot that mean there. There should have been a mean here also. The mean of Sij is being considered as u upon l, and the turbulent kinetic energy is u square. Okay. So, given this, so this is what, so
what scale is considering on that is compared. If I'm talking about integral scale, in that case, the scale of ui prime, uj prime won't be the same as the scale of the velocity that is
no, yeah, yes. No, but then for turbulence to be sustainable, the turbulent velocity scales are of the same order as the mean scales. So turbulence, when I say turbulence, I'm talking of fluctuations. So the fluctuating scales themselves are not small. If they were small, then turbulence would have died down. See the fluctuating scales. So overall ui prime average is 0. But if you look at the fluctuations and compare it with the mean velocity, it may be 0.5 times, it may be 0.2 times, but it can't be 0.0001 times the mean velocity. Because if it was very small, then obviously turbulence would not be there. It would be just u. U prime would be nearly 0.
So my contention with the representation of rho ui prime, uj prime, Sij
Yeah.
as rho square my inability to understand how ui prime, uj prime can be
So,
the key dimension
uh,
why
see, Sij in turbulent flows, we said that Sij is basically the dui by dx, du1 by dx2, whatever it is. So suppose if there is a linear shear, then obviously du1 by dx2 is known, whatever is u1 at the top minus 0 divided by x2. That is just a constant. So what we are saying is that is of this order, but the turbulent velocity also is of the same order as the mean velocity. Probably it will come more, this thing is in a gradient form if you expand in a Taylor series. Mean of u1 plus du1 by dx2 delta x2 If you look at the second term about the mean, so that is what the fluctuating term would be. So anyway, let's think about it. We'll continue in the next class from here. Next class will then now. So this tells us that we have to move to the kinetic energy equation. So by then at least, अच्छा अब कल का क्या करना है? ये तो चला गया, but we can. Do we meet to how many?